Here, at the end of All Things Organic Chemistry 1, we finally get a chance to talk a little spectroscopy. Today we'll talk a little bit about UV Vis spectroscopy, since we just talked about conjugation. At the very end, we'll get to talk a little bit about infrared spectroscopy and vibrations. But first, let's collectively recall from general chemistry that light, or electromagnetic radiation, has wave properties like wavelength and frequency. Frequency and energy of the light are directly related, but wavelength and energy are inversely related. That means that the shortest wavelengths of electromagnetic radiation, gamma rays, will have the most energy. Conversely, the longest wavelengths of electromagnetic radiation, radio waves, are going to be the lowest energy. So ultraviolet light, which has the shortest wavelengths, or shorter wavelengths than visible light, will have higher energy than visible light, which in turn has higher energy than infrared light. This also means that the light coming off of a purple car is higher energy than the light coming off of a red car, which may not seem like a huge factor of central importance until you have a 2-year-old. Light can interact with molecules, atoms, nuclei, and electrons in many different ways, depending on its energy. The highest energy radiation can actually change nuclear stability. Lower energy radiation than that can eject inner electrons and tell us a lot about the lower energy orbitals of an atom. There's some really cool spectroscopy here. Lower energy UV and visible light tell us a lot about bonding electrons, which can be useful for looking at molecular structure. Obviously, we'll talk a lot more about this in this lecture. Infrared light tells us a lot about rotation and vibration of molecules, which can be really useful for looking at symmetry and functional groups. Microwaves can rotate molecules. That's how we heat them up in a microwave. Longer and lower energy wavelengths still deal with modifications to spin, either of electrons or of nuclei, which can give really useful information that we're going to need to wait until after Christmas break to hear about. Okay, so back to UV Vis. We know that molecules are full of orbitals, both occupied and unoccupied. Any movement of electrons from a lower energy orbital to a higher energy orbital will require energy. It will absorb light. The more energy that is absorbed, the shorter the wavelength. So for bonding electrons, the highest energy transitions show up in the UV region, while the lowest energy transitions will show up in the visible region. We know that pi bonding orbitals are usually the highest occupied molecular orbitals where present, and our pi antibonding orbitals are usually our lowest. Movement between these orbitals will be the lowest energy. But a carbon-carbon double bond doesn't allow for a low enough energy to show up in the visible range. We need something with more conjugation to move things into the visible range, like beta-carotene conjugation. If we look at the left side of the table shown, we can see several examples of pi systems that contain only 2 electrons. The lambda max that is reported refers to the wavelength that is the highest intensity. This means that the most electrons will be making this transition, which often, but not always, is the lowest energy transition. Each of these unconjugated systems have lambda max values well inside the UV region. Notice that the pentadiene and the hexyne have similar lambda maxes. The pentadiene isn't conjugated because of the sp3 hybridized central carbon, and the hexyne is not because it has 2 separate pi systems. In the middle column, we begin to see conjugation between the 2 double bonds, which results in higher lambda max. In the right column, we see that more conjugation continues to raise the wavelength of lambda max, implying lower energy. We also see that carbon-oxygen double bonds allow for an even higher lambda max. The bottom molecule, beta-carotene, is highly conjugated and the lambda max is much higher, in the blue range, so we see this molecule, named for carrots, in the red-orange region. We know that conjugation increases lambda max. If we look at the molecular orbitals for the conjugated system, we can begin to see why. A single unconjugated pi molecular orbital stabilizes and destabilizes moderately, and the transition in energy between the HOMO and LUMO is relatively small. When we add conjugation, the most stable orbital is even more stabilized than before, but the next most stabilized orbital is less stabilized. It moves higher in energy, which makes the HOMO and LUMO closer together, and the change in energy lower. This continues as we add more and more conjugation, so the HOMO-LUMO gap becomes lower and lower in energy. Lone pairs are often higher in energy than bonding electrons since, big surprise, they are not stabilized by bonding. Lone pairs on an atom that is part of the pi system can easily make the transition to the LUMO, and in many cases allow for much lower energy lambda max values. Remember that the LUMO of most molecules is an antibonding orbital. Moving electrons into this orbital actually can break a pi bond. Such is the case with the isomerization of cis-retinol to trans-retinol in your eyes. Light comes in and is able to break and reform the pi bond into the more stable trans form. This molecule inhabits space differently and changes the form of an enzyme to both signal the brain and trigger the release of the retinal. This is literally how you see. Light is absorbed by retinal and converted to a nerve signal when it isomerizes. Much of the time, we are mostly interested in UV Vis spectroscopy for looking at concentration. We can't measure concentration directly, but we can measure the ratio of detected light to incident light, or how much light we can see with the sample in the way versus how much light we can see with an empty or blank sample in the way instead. If we express this ratio as a percent, we call it percent transmittance. Our UV Vis instruments will scan across wavelengths and measure percent transmittance at every wavelength, but it's different at each wavelength. As we scan across the wavelengths, we'll find a broad area where there is a percent transmittance that's lower. This generally corresponds to one transition, and they're broad because the energy for that transition changes slightly as the molecule vibrates. Hypothetically, there are an infinite number of wavelengths, but machines can only resolve wavelength to a certain precision depending on the machine. The important thing here is that we scan in small bits to get the large spectrum. While percent transmittance is directly derived from our measurements, it's not actually very useful since it isn't linear with respect to concentration. If we take the negative log of percent transmittance, though, that is linear. And we call it absorbance, which we usually indicate with an A. The percent transmittance here that we use in this version is the decimal form, so numbered between 0 and 1. This absorbance is very useful because now we can create a relationship between the concentration and the absorbance, the Beer-Lambert law. The absorbance is directly related to concentration of a substance at any given wavelength, and the slope is equal to the length of the light through the sample, usually 1 centimeter, and epsilon, an absorptivity value whose units cancel out length and concentration. This Beer-Lambert law is among the most widely used equations in chemistry because it allows us to use light to tell us concentration in a sample.